we have the concept of divisibility. We say that an integer b divides a, that we write as this, b divides a, if there exists a number k, so that this holds. And remember now, when we say number, we mean integers. So if a number b divides a, there exists a number k, so this is true. For example, we have that 3 divides 6, since there exists a number, and that is 2. So that 2 times 3 is equal to 6. Since there exists a number here, they divide. But we have that 3 does not, and you write like this, does not divide 7. And that's because there is no number that you can multiply 3 with that will give you 7. Then you have to have a remainder. But then it's not divisible. So if you're divisible, the remainder should be 0. Note that we have that 3 divides 0. Since we have that 0 can be written as 0 times 3. So there exists a number here. But 0 does not divide 3. Because there does not exist any number that you can multiply 0 with to get 3. So 0 does not divide 3. Does 0 divide 0? Then mean, is there any number that we can multiply by 0 to get 0? Yeah, then any number would work here. So it could be 1 or 0 or whatever. So this could be any number. So therefore we consider this as undefined. So this is not defined. So we don't say that 0 divides 0. Instead of saying that b divides a, then synonyms is that b is a divisor in a, or b is a factor in a, or that a is a multiple of b. So those are synonymous terms. So instead of saying divisible, we could say that. Divisibility basically means that if you have a division that gives you a remainder of 0. So you have that, let's assume now for the moment that b is not equal to 0. Then we have that if b divides a, then that's the same thing as a divided by b is equal to an integer. Okay, so b divides a means the same thing as a divided by b is an integer. That is no remainder here. So this means the same thing. So these are equivalent. Let's take an example. So since 12 divided by 4 is 3, and 3 is an integer, this is not a decimal number, then it's the case that 4 divides 12. But since we have that 13 divided by 4 is equal to 3.25, and that's not an integer, we have that 4 does not divide 13. Instead of writing it like this, we could just as well write like this. If b is not equal to 0, then we have that b divides a is equivalent, means the same thing as a divided by b give remainder 0. So that means the same thing as that above. Having divided divisibility, we can prove some theorems having to do with divisibility. So let's look at the theorem here. It says that if you have a dividing b, a divides b, and if b divides c, then it follows that, we should write here, if a divides b and b divides c, it follows that a divides c. So that's the theory. So how can you prove that one? Before we prove it, let's take an example. So we have that 3 divides 6, for example. And we have that 6 divides 24. So 3 divides 6, and 6 in its turn divides 24. Then it follows from this theorem that 3 must divide 24. And that's true. So that's a true instance of this theorem. So let's give a proof of the theorem. So we want to prove that if this is the case, then this follows. Okay, so we assume that this is the case. And per definition, that means that B is equal to K times A, where K is some integer. It means that there exists some integer K, so we can write like this. That's the meaning of that A divides B. And we also assume that B divides C. That means that there exists another integer, L, that L times B equals C. So this is means the same thing, and this means the same thing per definition. So this is the definition on that one. Okay, so we have this one. Now we want to prove that A divides C. Okay, but then we have from here now that we can exchange this expression. We can substitute it here. So we replace B with this, and then we get this. And this that stands here, that's an integer. Because if you have two integers and multiply them, we must get another integer. So let's call it m. So we can write this as an integer m times a. So we have that c is equal to an integer times a. And that means that a divides c. The meaning of this is that a divides c. That's the per definition. So now we have proved that if this is the case, A divides B and B divides C, then A must divide C. And that's what was stated in this theorem. And this is the proof of that. We see that the focus here now is more on proof than earlier. In the previous lectures on the number theory, the introduction we had, where we focused more on concepts and understanding and calculations. Here we are focusing more on theorems and proofs to be able to prove things. So let's look at another theorem having to do with divisibility. Okay, another theorem is that if A divides B and A divides C, then it follows that A divides B x plus c y. And here x and y are arbitrary integers. Okay, so if A divides B and A also divides C, then we know that A divides any sum here, any combinations like this. Okay, so this may be not so interesting in itself, but this theorem will be interesting or useful when we try to prove other theorems. So it's mostly interesting in that sense. But let's take an example to show that it's true. Or I'm not sure it is true, but how it works. So we know that 3, for example, divides 6, and 3 also divides 15. Then according to this theorem, then we know that 3 must divide any combination of 6 and 15, like this. So here we could choose any two integers. So this must hold since this holds. Okay, so that's the contents of that. For example, let me choose some random here. Let me choose x equal to 8 and y equal to minus 2, just to choose something. So let's put it in here. Then we get that 3 should divide 6 times 8 plus 15 times minus 2. Is that true? Okay, let's check. 6 times 8 is 48 minus 30. So this is 3 divides 18. And that is true because 3 times 6 is 18. So you see here that if this is the case, then 3 divides this sum. For example, if you choose 8 and minus 2. But you could choose any other number to integers than this and it still would follow. So that's the contents of this theorem here. So let us prove it. Okay, so we assume that A divides B and A divides C, since those were the preconditions in the theorem. And that means that B is equal to K1A. Because the meaning of this is that there exists some number K that we can multiply by A to get B. And the meaning of this is that there exists some number K2 that we can multiply by A to get C. So this is just the meaning of the definitions. And here K1 and K2 are just some integers. Now let X and Y be arbitrary numbers. So let X and Y be arbitrary. Then it is the case that we can, let's form this expression. We just write it down. Here we have chosen any X and Y. Then we can write down this expression, because B and C was given here in the precondition. This is just writing down an expression. We can rewrite this now because we know that B is equal to this. And C is equal to that. So we just replace that into the expression. So we get this. Now we see that A is both here and there, so we can factorize out it. Then we have remaining K1x and K2y. What's written here is an integer. Why is that? Yeah, because integer times integer plus integer times integer must be an integer. So let's call that L. So we have arrived at that this can be written as A times an integer L. Okay, so that means that we have that this sum is equal to A times some integer. But that is the same thing as A divides bx plus cy. And that's what we wanted to prove. So now we have given the proof of the theorem. Let's prove another theorem. Again, having to do with divisibility. So our main focus here is to learn theorems, but also train on proofs. So the theorem is that if A divides B and A does not divide C, but here I should have a vertical line, A does not divide C, then it follows that, then it implies that A does not divide B plus C, the sum of the two numbers. So this is the theorem that we want to prove, that it's always true. So if you have that A divides B, but A does not divide the number C, then A does not divide this sum. Okay, so let's take an example of what it means with concrete numbers. For example, it's true that 3 divides 6, but 3 does not divide 7, for example. Then according to this theorem here, then we know that 3 should not divide 6 plus 7. Is that true? Well, 6 plus 7 is 13, and 3 does not divide 13, and that's true. So this is true now in this instance. So we see that for these numbers, the theorem is true. But now we want to prove that it's true always for any numbers A, B, and C, fulfilling these preconditions. So now we want to prove it. Now we want to make a proof by contradiction. And remember now that we assume that A divides B and A does not divide C. And we want to prove that it follows then that A does not divide B plus C. So let us do a proof by contradiction. And that means that let's assume that this is the case. But let's assume at the same time that this is not the case. So that means that let's assume that A does in fact divide B plus C. So we assume that this is the case and also assume that this is the case. And then we will show that it follows a contradiction or something nonsensical. Okay. If this is the case, then it must be that B plus C is equal to some number times A. That's just the definition. Okay. Then according to the preconditions here, then we have that A divides B. And that means that B can be written as some integer times A. Okay. So let's take this expression and substitute this in here. So then we have that L times A, this one, plus C equal KA. Okay, so this must be the case. We can re-express this in the following way. We can write C on one side if we subtract LA on both sides. Then we have like this. And here we can factorize out A. So we have arrived at this. But what does this mean? It means that C is equal to an integer times A. And that means that A divides C. So that's the meaning of this. But we assumed in the beginning that A does not divide C. So now we have arrived at this contradiction. A cannot both divide C and not divide C. So that's now we have proved by contradiction. So what we did is that we assumed that this is not the case. We assumed that this was true because that's precondition. And we want to show that if this is not the case, then this must be the case. And if this is the case, we have this. And from this, if we add the condition that A divide B, because there was a precondition, then it follows like this. And this we can rewrite to mean that A then must divide C. But we assumed in the beginning that it did not divide C. So we arrived at our proof by contradiction. That means that this cannot be true. This assumption cannot be true. And that means that this must be true. So we have proved that this is true by assuming the opposite and shown that that leads to a contradiction. So this is a concrete example of a proof by contradiction. And if you want to remember what different types of proofs there are, you can look up here.